It's the cost of admission. We don't charge dues, but you do have to participate in this. So with that, I'd like to hand it over to Bill for absolutely one of my favorite features in these meetings, and one of the many, many things that I'm grateful to Bill Ragsdale for.
Great, thank you very much, Kevin. Do we have any participants in our challenge today? Say your names slowly so I can jot them down. Do we have any participants that would like to present on the challenge is computing large n factorials?
I will.
We have Brad, very good. Any more?
Hello, can you hear me?
Yes, Vito, are you going to participate?
Actually, for some reason this morning, my desktop cannot see my USB microphone, so I'm unable to share a screen. So I will leave somebody else do the presentation for me if it's possible. Because right now I'm talking with you using my phone and I can't share any screen with my phone.
Does that mean you are participating or not participating?
Well, I'm just watching because I'm unable physically to share a screen to show you.
Can you send your code to someone?
Yes, I sent it the beginning of the week.
Yeah, I have it.
Yeah, so since I cannot show it, well, I'm unable to do the presentation myself. I'm very sorry.
Dave, can you put the stuff up on and share your screen? Or Vito, can you talk about what you see on on Dave's screen?
Yeah, I can. Yes.
Is that reasonable, Bill?
We'll give it a try when we get into the rotation. We'll give it a try and see.
Okay, we'll see.
Good. And
okay,
we have one. Now is not the time. we're not there yet, but it's good.
Okay.
It's good. We're getting okay. We'll get you in there. And we have also a Russian gentleman. I don't know his first name. It's Vidovic. Is it Antonio Alexei? Anyway, we have a presentation from him that I will give because he is in a difficult time zone in Japan, and this is
that's me.
Oh, it's
I'm
you.
sorry, that's me.
Very good.
That's me.
Then let us try this. Let us try this. I have prepared your talk in the form of slides, and let us see if you can show, if I can show the slides and you can narrate. Let's try that because the slide presentation is very organized and you should recognize it. Will that work?
Okay, let's try. We never rehearsed anything, so let's try.
Good, very good. I thought the material was absolutely excellent, and so I prepared the slides. Do we have any other presenters? Come now. All right, we will segue into our presentations. First up, let's go to Brad Nelson, please.
Let me go ahead and sorry about that. Share my screen. All right. I went at the problem sort of just banging at that the big num approach, and I just gave myself. I figured, well, you know, 100 times itself would be 200 digits, so I gave myself 200 places of workspace, and I decided to use a single byte per digit to make it easier to later emit the result. I created a space for those digits, created a word that initializes the digits to a 1, it was all zeros and then a 1. And then I have a word that loops through and finds the first non-zero digit and then prints each of the digits. I have a single place multiply step that moves along. I should point out I'm storing the digits in least significant order. So going, the lowest digit is at the front, and so I've got a sort of a multiply carry step that takes the current position and whatever number you're multiplying by and the current carry and applies it and then moves on to the next spot. And so then I'm able to take a single cell value and loop through all of the digits, applying that operation. And then factorial becomes initializing things to 1 and then looping through and multiplying by each of the digits in series and then printing things. And just for fun, I've got it, let's see, I'm going to reboot. I've got, I don't know if that's visible. I've got things running in on this ESP32, and I put the code into a block, and I'm going to load that block, and then I'll do 100 factorial. And I need to, and then I need to print my current digits. And there it is. Back to you, Bill.
Yeah, can you go back to the concluding screen? I want to see the number with all of its trailing zeros.
Oh, yes, let me do that. In fact, let me zoom in on it so you can see it a little better. I've at least compared that against what you get on out of Wolfram Alpha.
Where's your result?
Right down here.
There we go. Starts out 933 and ends up with 24 zeros. Very
Yep.
good. Passes the credibility check. Thank you. Thank you very much.
There you go.
Thank you. Okay, very good. Now we are going to have a real exercise here where Mr. Vujovic is going to give a talk from slides that he has never seen before. So let me bring those up.
All right.
Hold on, let me bring it up. But if you could explain what you see on each screen, since you wrote the code, and then tell me when to advance to the next screen.
Okay, let's try. Oh, by the way, I talked with Greg and he says hello.
Oh, wonderful. So there is an exact solution for our challenge, which is to do the number 100 factorial. And so take it away.
Okay. Okay. Am I supposed to comment on this title? Fair enough. So the problem was to compute factorial 100 exactly with extra bonus for counting the trailing digits. This is the high-level word. So we're just going to take a number on the stack. We're going to initialize the buffer pretty much in a way that resembles a little bit what was just presented, actually. We're going to compute the factorial by iterating, so it won't be a recursive implementation that will be a loop from this number to 1, multiplying by the previous, etc. For each iteration, we're going to have pretty much the same thing. We're going to have one digit multiplied by the current multiplier, added to the previous carry, and we're taking the 1 or 2 digits which result with we set the current digit to the buffer, and then we prepare the carry for the next digit, etc. We will see in detail in a second. And print factorial is just a loop with emits going from the end of a buffer to the beginning of a buffer. Very, very raw, and obviously very fast too, but yeah, it won't be visibly faster than the other one. So this is the initialization of the buffer. It's just an area of 255 bytes preceding by a length byte, which should be enough for factorial 140. That's why there is a hard test for 140 in the middle, which aborts with an overflow error if it's more than that, because we don't have reserved enough space. That's not very elegant, but yeah, the problem was factorial 100. So that's just this. It's every factorial for every number between 1 and 140. And by the way, as you will see in the next definition, I guess, you can calculate factorial 0, which is set to 1, and factorial of a negative number, which is set to 1 as well. It won't trigger an error because it's too much work to just print a message where you can just have 0 and negative set to 1. And good luck if you have this problem anytime in the future. Anyway, so basically you put 0 as the length in the factorial buffer. If the number you ask for, it initialized using the number you want to calculate the factorial for, by the way. So if it's 0 or negative, you just put 1 there. That means that the initial input will be 1, and you will have a factorial of 1, okay? There is a low-level word which adds 1 or 2 digits in a low weight, high weight order to the buffer. It will be used during the calculation as well, as you will see. This quickly initializes the buffer. I mean, there's not much talk to do about this one, I guess. Everybody understands it, this small piece of code. I talked a lot about a handful of lines of code that everybody understood at the first read, I guess. Well, anyway, let's go to the next one, unless you have something to add. So this is, again, a high-level word. Yeah, okay, fair enough. So if a number which was initialized previously is more than 1, then we will do the effort of looping from 1 to that number, -1. What the fuck? Yes, exactly. From 1 to that number to calculate the factorial. Usually I prefer to present from a low level to the high level. That's a bit strange for me here to do the reverse. Anyway, that's fine. This is intermediate level. So as you can see, it's pretty much, it resembles a lot the previous code which was presented. We're going to loop through one iteration, one line, I guess, using a word which is called fact atom, which is just getting the previous carry, multiplying the current digit by the current multiplier, adding the carry, then getting the digit which results and putting it in its current position in the buffer, and extracting the carry for the next atom. So an iteration is actually an iteration of iteration. The low level, which I call fact atom here, is that low level thing that we'll probably see in the next screen. And this one is actually what happens in one line. I mean, one entire add, carry, multiply, add, carry, get, carry, etc. until the end. So the first part of a loop is actually replacing the digits with a new result, and the last one, if there is a carry left, we just add that to the buffer, which means that the buffer is going to grow. The buffer contents are going to grow. The buffer is a set size, sorry. The result is going to grow naturally, iteration by iteration, by 1 or 2 digits. That's it, I guess. So this is the low level. So this is extremely easy to understand, I guess. You see, on the stack, we've got the previous carry, the multiplier, the current digits, and we expect to have the next carry as well as the result on the stack. It's very, very easy to read. Again, I'm not sure if there is matter for a comment here. I would have presented that in the reverse order, actually, from the low level to the high level. Mine, it's easier to understand that way. But anyway, that's fine. If there are any questions, go ahead, but I doubt there is any question about the multiplication and addition here. As you can see, we just divide by 10 once in order to get the carry, and we remove the carry from the result to get the digit, which is the result, the current result. So that's all, and pretty much what's inside the comment. So this is the lowest level, which is used both in the initialization and at the end of one iteration. As you can see, we get the length byte, which is always at the beginning of the buffer. So a little bit overkill. I could have put that in a separate variable, but it was funnier that way. Then we check if we want to add is 1 or more digits than that. So if it's 1 digit, we just store it at the current free location, and we store the new length at the beginning of the buffer, or we will have to separate into 2 digits that we will add and then add at the next location as it's high-endian notation anyway. And we update the buffer length again at the end. As you can see, there is a store digit, very low level word, which does just that. So then again, there is not much magic here. Oh, I noticed that you like to put the semicolon at the end of the next line. I like to put it at the beginning of the very last line so that I can align visually the beginning of a definition and the end of a definition. That's funny. Okay. Sorry, I'm talking a lot. Print factorial is just a word which is defined to display very quickly the contents of a buffer as a decimal string on the screen. So you take the length, you just loop through it from the end of it. Of course, if there is nothing to display, that means that if the length is 0, you display nothing to display. Otherwise, we're just going to loop from the end of a buffer, which means that the last used digit of the buffer, not the 255th digit, of course. And we're just going to fetch the current byte, add 48, which is the ASCII code for 0, and we emit it on the screen, and we go again until we have first byte of the buffer, which is actually the unit byte. We store in big Endian. That means that we must display from the right to the left in order to the right of the left to the left of a buffer in reverse order, so that we have a displayed number in its human readable state. That's it. So we go back to the high-level word factorial, takes one number on the stack, initialize it in the fact buffer, then call the compute factorial, which is just going to do the iterations we talked about, iteration over multipliers from n to 1 if necessary, and inside this iteration be what I call atom, which is just going multiply, add, carry, multiply, add, carry, etc. This is very easy to read. And print factorial, which is the first display routine here. That's it. There was also another word which I did, which counted the number of zeros. This is going to be extremely easy. We're going to go to the buffer. If the length of a buffer is not 0, we're going just to count the number of 0 from left to the right. So it's just a loop, while loop. While it is equal to 0, we add 1 to the counter, and that's it. But that was not even worth mentioning, I guess. Okay, that's fine. Do you have a screen with, yes, you have it. Okay. CR 100 factorial, which is it, okay. And I guess you don't have a screen with the count of the number of zeros, because I did that after the fact. I realized, yeah, there is an extra credit if you count the number of zeros. So I added a word 2 to count the number of zeros. Must have been the next mail I sent. Anyway, that's fine. It's very easy to do. So that's exactly the same number as the previous presentation. The code as wrote was longer, obviously, but I hope it was easier to read. But the algorithm was the same. Yes, it was roughly the same. And also the representation of the data was also the same. So there is not much difference between both our codes, if you think about it. And sorry for being so verbose. It's less than 5 o'clock for me right now. So I'm just starting to wake up. Haven't had my coffee yet.
You're speaking to us from the future, from
yes,
early in the morning tomorrow.
Yeah, it's Sunday morning. Although I've been driving 11 hours yesterday, so I'm still a little bit fuzzy because of that. Yeah. Yeah, so sorry, that was very simple. Yeah, maybe at one point I will redo it, but on a GA144, because that's an awesome machine too. Why not?
Thank you for that presentation. I appreciate that he's in, SVFIG is in Japan at the moment, and the time is very inconvenient. So we thank him, and he did a heroic job on giving a very well stated presentation from slides that he had not seen before. So
yeah, if I could advance a remark here. I would have presented it in the order of the simplest words to the most complex words, actually, not this other way around. The way that you define words in force, anyway. My feeling is that it's easier to understand when you go to the atomic level to the complex level. But that's just a personal remark, of course. It's a matter of taste. That's all.
very good. Thank you. And now I will wind up with my presentation. Get to it here. And I originally created this as what I'm calling poor man's floating point. It's how to handle large number calculations if your computer does not have, your fourth system does not have floating point available, as a very quick and dirty method and approximation. So in this, we're attacking the same goal, compute 100 factorial. And then I want to do a check with floating point math, which I did have on my system. And then to calculate the number of trailing zeros, it turns out this is an interesting academic exercise. And then finally, extra credit would be to compute 100 factorial exactly, which we've already seen done quite well. So the pseudocode for my solution is to set up some variables that simulate floating point, set up a loop that runs from 2 to the desired factorial. And of course, it has to be n+1 because of the way do loops are done in fourth. We start with an initial value of 1, which is our final product. And then we loop n times, each time increasing the index by 1. The key factor is we have to adjust for overflow because I'm on a 32-bit fourth and the number grows past 32. We have to adjust for the overflow, which is the key to the whole process. And finally, we loop till completion. So our variables are actually simulating a little floating point register. The floating point consists of the significand, that is the integer portion, and then the exponent, the power of 10 as the exponent, and then finally our input number. So a little setup code says I'll put 100 into the input value and set the significand and the exponent to 0 and begin. The output is very simple. It's built on the fourth output words. Once we develop our values, we take the exponent, convert it from single to double, print out the number of digits. We then insert an ASCII E, so we're going into exponential notation. Then we take the significand, convert it to a double number, convert its digits to ASCII, and then type the output. The overall wrapper, I have the word by integer, which does the entire process. It does the setup of the variables. It processes the input, and then dot output displays the output. The key work is done in the process word, and you see it's simply a do loop that runs from 2 to n+1. And adjust is where the work is done digit by digit by digit. We'll look at this in steps. The adjust part begins by doing a double number division. The while checks for overflow. If there's an overflow, then it adjusts the values on the stack and saves the exponent and the and then finally at the bottom after the repeat part, some adjustment is done by nip cutting away some of the values, and then the integer portion is stored in significand. So in the looping portion, we store the exponent. When we're all done, the final value is stored in a significand. Here's a check as a floating point routine. We start out with a floating point number of 1, then take our input number, set up the do loop. In this case, we go from a single number to a float, do a floating point multiply, and then FE dot prints out the floating point answer. So that's our floating point check. Here's our output. Now remember, this is approximation. We're using binary coded decimal numbers, or pardon, we're using pure binary numbers, but our significand is the limit of 32 bits. So the full process of setup, process, output gives us the 93326 times 10 to the 147th. And I'll make a note in a moment on rounding. The check by floats, you see, likewise is 93.326 times 10 to the 56. And at the bottom right is a internet check. So we see how it's done where it's normalized to a 9.3. I made no effort to normalize my numbers. That would be if this was going to be used over and over again, we'd work out to normalize to the first leading digit. And this is the exact solution that I got from Wolfram's website. And it's the same as we saw from Vidovic's solution. The question is, how many zeros are the trailing zeros? This is a little academic exercise, and the solution is that you find out how many factors, how many times is 5 a factor of the input number. So if you take the 100 divided by 5, you'll see there are 20 values, 20 factors of 5. And then from the resulting quotient, divide that by 5, and there are 5 more 5s in the quotient. Gives us a total of 24 zeros. And this is fourth does that. It's a zeros question mark. Is a begin until loop that divides the input number by 5 until there is no quotient. And the output at the bottom, 100 zeros question mark, and it says the number of trailing zeros is 24. Now I'll make a comment on the rounding. You see my calculated number is somewhat smaller than the floating point solution and has a fewer number of digits of resolution. And the reason for that is that my rounding is done on overflow is done by truncation. So this is always rounding towards 0. Once I got into this, I realized this rounding error was not appropriate. And instead, it would be better to round toward, it would be to round, would be to round down if the least significant is odd, and then round up if it's even. And this will then be rounding toward the 1/2 value. And so the second thing I discovered in my process was that I set up the fourth loop from 2 to n, which does not actually make the calculation for the final value of n. So I was off by 100. It never made it went from 2 to 99, never made the last multiplication. And I was off by 2 orders of 10. So I scratched my head for a while on that. And I realized that I had to adjust the fourth loop, and putting a simple 1 plus n fixed that. So credits, I had help from Google and from Wolfram on the full values. And it also revealed my little do loop area. And since I'm using Win32.4, I always thank Andrew McEwen and Tom Zimmer for creating Win32.4 and the Europeans who did the update. And this is posted at GitHub. So if you would like to go in and see the code or the slides, they are available at GitHub, and they will also be available on the 4th intergroup website. So that concludes our challenges. Do we have any questions? I'll make them simple. Any questions? Simple questions. Like, how did he do it? And then why does he do it? Very good. Back to Kevin. Thank you for your rapt attention.
All right. I'd like to unceremoniously ask Brad to pull a plug on the recorder, and we'll see you next month. 4th Saturday of January, 9:30 a.m. Pacific.